Thanks so much, Holger. And a huge thank you to the Bavarica team for sort of the organization. I don't know if everybody got a chance to hang out and join the keynotes and sessions yesterday, but the bits that I was able to catch were absolutely fantastic. It's always exciting to have these kinds of things, especially in a time like this where life is a little bit crazy. So hopefully everybody is staying safe in all their respective homes. I am coming to you today from San Francisco in the US, where I'm based out of. And like Holger said, I am at Splunk. I am what Splunk calls a distinguished engineer. It mostly means that I'm responsible for technical direction over different slices of our product portfolio. One of the parts of that I'm responsible for is our stream processing infrastructure, which is heavily based on Apache Flink. So we're pretty heavy users of Flink within Splunk. And actually today, what I want to talk about, and we're going to see how this goes over. I always want to go deep into the details, but really I wanted to focus today on the evolution of the data architecture and sort of the process from bringing Splunk through from being sort of primarily batch and sort of schedule oriented through to being a more sort of real-time and stream processing focused data architecture. So I won't get into a ton of the details of Splunk, even sort of what the Splunky details of that. I'm mostly going to focus on the actual data infrastructure. Hopefully this is directly applicable to everybody in the audience today. Like Holger said, I'm happy to take questions and stuff like that, or to connect. Please feel free to reach out to me. My contact info is there. So just high level, if you're not familiar with Splunk, just a tiny bit of context. Basically, Splunk is a platform that is sort of fully integrated, that has support for the collection, storage, query, and analysis of both event, discrete event, and time series data. People probably know us, as like quote unquote log search. Certainly that is a huge chunk of what we do. But there are sort of other kinds of events too. So pretty much anything with a timestamp is sort of fair game for us. For telco people, for instance, we deal with a lot of things like call detail records. A call was initiated, a call transferred, radio towers, call disconnected or failed for some reason, all of that kind of event data. And then of course the time series stuff, which is, metrics for IT operations and sort of counting things and all those other kinds of things. Splunk's kind of like secret sauce is that it has a ton of query time processing features. So there's a huge emphasis historically on, internally what people say is like schema on read. So basically extracting fields, doing transformation and things like that at query time rather than at ingest time. And today what we're sort of talking about is kind of balancing that seesaw a little bit by adding a bunch of ingest time functionality. Splunk has a core platform, that is sort of this fully integrated platform, both the underlying data infrastructure and the application that runs on top, which is sort of a horizontal experience for querying data and exploring data and things like that, dashboards, alerting, stuff like that, but also increasingly has what I would call sort of domain-specific applications, things like systems for IT operations, applications for security analytics, insider threat detection, like all these other kinds of things that are a little bit more focused on a specific domain. So we sort of have this gamut of generic use cases, which are just, I want to, sort of tear my data apart. And then these more specific cases, which is like, I'm looking for insider threats and things like that. So generally speaking, in terms of like the classes of workloads that we see a lot of this ad hoc query, and this can be both from humans and from applications. Humans are like people actually typing queries in. Applications might be more like somebody loading a dashboard that has like 10 charts on it that all sort of have some query infrastructure on the back end. Scheduled queries make up a huge part of what we do. Splunk internally, has a bunch of indexes and things like that, but also has materialized views. Basically, it's not quite what we call them inside of Splunk, but to the outside world, they mostly look like materialized views, where they're pre-cooked, views of data that accelerate certain kinds of queries or provide more structure for well-known data sets, things like that. So scheduled queries are all about building and maintaining those views. They are the way that we express application processing. So basically batch processing in a lot of cases. And our alerting system, which is a big part of, what people tend to use Splunk for, when they see something in the data, they want to do something, whether that's something as simple as send an email or an SMS or something like that, or as complicated as, triggering automated remediation and flipping firewall rules and all these other kinds of things. All of that is based on scheduled queries. Splunk does have a real-time query facility. It's used for sort of like live tail kinds of use cases. I want to watch my build, or I want to watch a deployment happen. But also application processes can use this as well. So today, again, like what I'm talking about here is really what happens as we add Apache Flink to sort of our platform primitives and our sort of toolbox here. So in order to sort of help you understand, why this makes sense, and to sort of give you a little bit more color about sort of the classes of workloads and what was important to us, it kind of makes sense to go back about 2.5 years ago. So what I'm describing now is roughly what Splunk looked like about 2.5 years ago. This is a very, very, very simplified architecture. Unfortunately, it's not quite this simple. But basically, all data lands in an index, again, 2.5 years ago. Data coming in from various kinds of connectors, agents, or what we call forwarders internally, which are sort of sitting on boxes, pulling data and metrics, passing through an index or pipeline that sort of does all the stuff that you would expect for index building, and then deposits that data into indexes. And the decisions about sort of routing and all these other kinds of things are either defined by the sources or by sort of rules that exist inside of that index or pipeline. Applications and platform services, and by platform services, I mean things like our alerting facilities and stuff like that, primarily use scheduled queries to build views of that data or to just process that data. So if you're an application, you have the ability to issue scheduled queries against an index. You can issue scheduled queries against a view, either a non-materialized view or a materialized view. And in the middle here in this diagram, you see that a query actually, this is the way in which we populate views or maintain views. So we query an index, there's some result set, and we actually insert that into a view. So this is basically also a low-level facility about how we perform view maintenance. So obviously there's a bunch of challenges with this that we sort of bumped into, just as, I'm sure a lot of you have in these kinds of patterns. Latency is one that we sort of talk about the most in stream processing. We sort of get wrapped around the axle about how fast this is. It's interesting, don't get me wrong, but it winds up being not always the biggest challenge. Sometimes the business is okay with some latency and stuff like that. Obviously, they prefer not to have it. But on the list of priorities, it's not always number one. But it is a thing that happens, especially in like the security space, where if you think somebody's doing something bad inside of the network, you want to kind of shut that down as quickly as possible. Polling query workload overhead, just the actual sort of mechanics of issuing all of these batch queries against the system. View maintenance, alerts or triggers, whatever you want, however you want to think about them, and like all this application processing is actually pretty substantial. And I'll sort of quantify that for you in a minute. And one thing I think we probably don't spend enough time on is sort of the programming model around just issuing batch queries, leaves quite a bit to the people developing those systems. So state management in particular is really nasty, knowing what you've seen, what you haven't seen, basically at least once, at most once, exactly once, kind of processing semantics. The failure and recovery semantics of that, which is sort of tightly sort of part of that state management challenge, is also just real. We see these kinds of things all the time. Within the query engine, Splunk is deeply parallelized, but outside, if you're issuing a query, you're basically getting one stream of data back. So like this, you have this sort of challenge of not being able to participate in that parallelization. Splunk has things like for custom search commands, basically you can push stuff into it, but it's not as, you actually have to like go and sort of like think really hard about how you do that. Optimization, orchestration of those queries, all these kinds of things are left, to the engineers, which can be really challenging for, at least from our perspective, it looked pretty challenging. Just to sort of put a little bit of color around that, I want to sort of use the polling query overhead thing as an example. Just to sort of give you a little bit more color on that. So like, how bad is it really? The answer is it's pretty bad. This is actually some anonymized real deployments at Splunk. I can't tell you too much about sort of what kinds of deployments and how big they are and those kinds of things. What we're looking at here is basically the raw number of queries that have been executed by different customers. And over some time period, again, like I can't unfortunately get into a whole lot of detail around whether this is per second, per minute, per hour, or whatever, but it's just a lot of queries. The total number of queries, the percentage of those that are ad hoc queries actually being sort of typed by humans or issued by applications like loading a dashboard, for instance, or scheduled queries, which is the highlighted column. So this is the column that is like stuff that could actually be replaced by stream processing. And just in this cohort, the P99 is about 94%, 95% of queries are actually scheduled. Even the P50, 63%, 64% are scheduled queries. So it's actually representative of a whole lot of the workload. So if you sort of step back and do like this sort of like, if we could do X, we would get Y kind of exercise. If we could move the view building or maintenance, alerting, and application processing to the ingest stream as data flows into Splunk, there are cases where we can get up to a 94% query workload reduction of the actual queries going to the query engine. And that means that we would have substantially more time for ad hoc queries, which is a huge, huge, huge deal. It's worth pointing out, by the way, in this slide around the schedule query, Splunk has facilities for sort of hard limiting the number of schedule queries versus ad hoc queries. So keep in mind that this actually might be a best case scenario. Like if you look at, there's one in here that's like almost exactly 33%. It's very likely that that customer has set 1/3 of their query resources to be reserved for scheduled queries. It could very well be that there are more scheduled queries that would run if they could. So we can get some pretty substantial gains back on resources for ad hoc queries, which is a huge deal to customers. That's not to say that processing goes away, just that as you push things to the stream for things that are looking for a bad actor over the last, doing event correlation over the last 30 minutes, those alerts wind up constantly hitting that 30-minute window rather than sort of keeping finite state machines and smaller state information. So like the actual cost of combing over that data set is pretty high. Of course, reducing latency to data visibility means faster time to action, and being able to provide a safer and more consistent and efficient programming model for our developers, both internally at Splunk and externally our customers, is actually a huge win. So those are things that we would really like to see. If we could let developers and end users of our system tap into that ingest stream and sort of actually be able to pull versions or curated streams off of that, we could wind up with deeper integration opportunities with other data infrastructure. For instance, we have customers at Splunk that have on the order of millions of agents deployed. So like everything in their enterprise is already instrumented. And all that data is coming into Splunk. And then they kind of go like, yes, but I want all, events of type X, all HTTP transactions also in S3, for some other business processing that I want to do. And, where, don't tell anybody at Splunk I said this, but maybe where they want to use a different tool or a different platform than Splunk. In those kinds of cases, we don't want to, really sort of trap the data. I mean, we want to be able to sort of integrate and support those kinds of use cases without them having to collect that data a second time. There's also all sorts of ingest time extension points within the system. And if we could support those, we would then be able to support more use cases. And this typically involves things like denormalization functions or domain-specific functions within the sort of ingest pipeline. If we could support additional ingest time functionality, like new kinds of operators that might not be sort of either built by us or sort of known by us, it's entirely possible that we could affect better data quality downstream. And I'll give you for instance, we see a ton of data coming in to our systems. I don't know about yours, where we have like malformed data, things that miss time, that have no timestamp, things that have a timestamp, but it's in the wrong time zone, those kinds of things. All of those kinds of data quality issues basically make that data unusable for downstream systems. Humans can sort of deal with that kind of variability, but like machine learning models and like all those kinds of things really choke on this stuff, right? You can wind up like doing really terrible things to models downstream of you. Data governance and control opportunities are actually really interesting, especially for global businesses that may have like multiple facilities, regions across the world, where they want to protect things like data sovereignty around certain kinds of data. GDPR comes to mind. So, a customer who operates globally may decide that they don't want certain pieces of German citizen data to leave Germany, or they may not want certain data actually resident inside of the US because they don't want, that exposed to like US government or whatever government really. Being able to shape and route and mask and transform data before it hits, the storage system is the way in which we can sort of, affect those kinds of policies. And then, of course, like DR and BCP and scaling primitives, if we can use the ingest stream as effectively the sort of transaction log. I think the folks over at Confluent talk about this model quite a bit. On the messaging side, this actually gives us quite a bit of opportunity to route the same data to multiple facilities for read replicas that are geographically local or sort of optimized for a specific use case, things like that. So, really, like, what would Splunk look like if we added stream processing as a platform primitive that was sort of deeply integrated with the system? Turns out there's a couple of phases to this that actually make sense. So on the ingest side, we looked at this and said, like, well, what if we focused on the actual primitives and just getting the infrastructure in the right place, and really focused on the ingest process? Ideally, we'd like to make this optional. We have a lot of on-prem customers measured in like tens of thousands. And so you kind of don't want to have to go and sort of, wake up all sort of, N thousand people and ask them to sort of deploy new software if it isn't sort of interesting to them. Doing this with minimal disruption to the current semantics. So basically trying to focus on cases where we can sort of exclusively get wins out of what we're doing is really where you want to be. So here, there's a little bit more detail on sort of architecture stuff. It's a little bit of a before and after. In this top chart, you see like parts of what I've shown you before, the connectors, agents feeding into our indexer services. Obviously, these things are all parallelized and stuff like that, but let's look at it logically rather than physically for a second. Indexers generating indexes, and then queries building, materialized views periodically, off those indexes. So what we've really done here is actually spliced into the space in between connectors and agents and all the sort of data sources and the indexer, and actually inserted some infrastructure here to provide this functionality. And so basically what we've done is we've added this concept of like a Firehose is sort of what we call it internally. And all this really is a pub/sub messaging topic that is the sort of aggregate of all the data sources that are coming into Splunk. And I'll talk a little bit more about sort of how we structure that in a second. And then we have our stream processing engine, which we call DSP. I'll talk about that in a second. This is where Flink shows up in our architecture. And then we have the ability now to use that engine to send data off to third parties. And so just a little bit more context, data stream processor, or DSP, is Splunk's Flink powered stream processing engine. It is both a technology for us, something that we use to power a bunch of projects or products internally. Is also a specific product that someone can buy and sort of use. I'm not going to get too into the details here, I'll just sort of give you the relevant parts. All of the connectors, inclusive of things like APIs and agents and all these other kinds of things, produce to this Firehose pub/sub topic in a common envelope. And that envelope includes a bunch of sort of interesting information like nanosecond precision timestamps and things like that. And then all of that stuff feeds into this stream processing engine, which has both system configured pipelines and user configured pipelines. So pipeline is sort of the thing that we expose to people. It primarily, there's some detail here I'm glazing over around optimization stuff, but it mostly corresponds to a Flink job. A pipeline is really one or more sources followed by 0 or more functions that do stuff to the data, and then 1 or more sinks. And obviously that functionality is parsing and routing and enrichment and filtering and aggregations, and joins and unions and all sorts of other stuff. We implement branching, just sort of pulling multiple sort of functions off of a source function. These functions can actually be written in Splunk's domain-specific language, which is SPL. We also have a native SDK that is Java, that handles all of the type checking and planning and optimization that is like very Splunky, and then ultimately winds up baking down to a Flink job, at which point we sort of hand it over to the Flink planner to do sort of the logical physical planning of the job. But we actually do a bunch of stuff before that to make sure that people don't build, wacky pipelines and stuff like that. This Firehose concept is actually like super useful to us. It does give us this common envelope for all of the data. There's a lot of information there that I think we talk about in sort of other public forums. If you sort of, Google around, you probably find it. But there's a body in this envelope that contains sort of any data type. It's sort of a union over a bunch of types. It can be bytes. It can be a deeply structured object. It can be a string, which is very common in Splunk, when we're dealing with like log data. So it could be all sorts of things. And then Splunk has this pre-existing concept, which is like source type, which sort of confers semantic knowledge about how to interpret an event internally at Splunk. We hang a bunch of information off of this. So basically things like field extraction is source type specific. So if you have a specific source type, we apply a bunch of rules to it. We sort of piggybacked on this concept inside of the Firehose. It's worked really well for us. This Firehose is actually represented as a source inside of DSP. So one of the sources that somebody can pick from is is the sort of big old Firehose, has everything in it. The more specific sources, like if we had a source that was like just your firewall data or just your Cisco firewall data or just your Amazon CloudWatch data or something like that, that is typically represented under the hood as the Firehose plus a filter that sort of narrows down the data to that specific type. And so there's a couple of patterns that have worked exceptionally well for us within DSP. And again, like these things, I think you can apply, you know, to any sort of Flink job. They're not Splunk specific. So the sort of upgrade of semantic information, we have cases where things enter with like a very generic source type, like it came from syslog or something like that. And really what people downstream care about are like firewall events, regardless of vendors or Cisco, you know, stuff or Juniper stuff or Palo Alto Networks, whatever, or just cloud firewall events or something. In those cases, we use the pipeline to effectively up-level the source type as we learn more about the events through field extractions and pattern matching and, you know, classification models and like classification systems and all these other kinds of things. So through a series of operations, we sort of up-level the semantic information, what we know about an event. And we also tend to preserve the unmodified version of that. So even though we're extracting a bunch of stuff, we can keep the original so that if somebody does want to like down level it and treat it as like a generic syslog event or something like that, or generic, you know, Linux audit D or something like that, like they can do those kinds of things. Obviously, things like routing are implemented as branches in a pipeline into a filter and sync pair. So basically forming what looks like a switch statement. You know, given the semantics of the engine, this is not exclusive routing. This is more like pub sub style routing, where, you know, non-exclusive routing, because you can send the same data to multiple places. We actually use that quite a bit. External functions use queues to produce and then consume from external systems. But I got to tell you, this stateful function 2.0 stuff that Stefan talked about yesterday is actually really interesting because it adds the state management and removes the sort of queue overhead. Even though it has some RPC overhead that's still lighter than what we have today. So I think the combination of these things to sort of loop in an external process is actually super, super powerful. I'm so excited to see what the community is doing here. We have this notion of group functions, which are really just fragments of the directed acyclic graph that we build that can be sort of inlined in the pipeline in various ways. So this is, like I said, if you have the Firehose plus a filter, this creates what looks like a curated stream of just a specific data type. If you also include things like field masking and anonymization functions, and you combine that with function level role-based access control, when people are building those pipelines, you actually get what amounts to efficient data limiting use cases where you're not necessarily copying the data until somebody is actually consuming it. So this has actually been a really interesting construct. We can, some of the stuff I'm talking to you about is stuff that like we're in the process of doing, or, you know, have done internally, but not externally. So like, you know, please don't read too much into any of this stuff. We are publicly traded. So like forward-looking statements and all that stuff. But if you sort of take away access from the Firehose and grant access to this group function that filters out certain information and only allow people to use that in their pipelines, now you have, you know, what amounts to sort of an efficient view over the stream that guards against access. So at the end of phase one, having sort of done a bunch of this stuff, what we wind up with is we get the deeper integration opportunities, we get the ingest time extension points and the support for additional use cases. The data quality stuff we can sort of address. The governance and control opportunities are huge for people sort of consuming that system. And you get the DR BCP stuff because you can send data to multiple places. It is eventually consistent, but But given the delivery guarantees that you have within the engine and the messaging systems, you have a reasonable set of constraints to reason about the sort of state of the data. So with the ingest time stuff in place, we can now focus on moving all of our application processing that is currently expressed in batch jobs upstream, because we have a place to move it. So really what we're talking about here is pushing those polling operations upstream or to the left in that architecture diagram, giving the developers a way to migrate those batch processes to the stream, either in part or whole. And I think this is interesting because some stuff makes sense to do at query time, but there are cases where we can make that life substantially easier. One case, in the security space is mapping IP address to MAC address, because you get lots of events that contain IP addresses, and what you really want to know is which device, which user. So you kind of want to marry that with MAC address, and like that mapping changes dynamically due to things like DHCP over some long period of time, and sort of having a version of that matches what the state was when the event was generated is actually sort of a really nasty problem. So denormalizing that kind of data in the process actually makes a bunch of downstream processing substantially easier. And of course, a number of these platform functions like alerting and view maintenance, making those streaming by default so that customers sort of like turn on the system and it just kind of does the right thing is actually really powerful. So again, now we have our sort of before, post phase one, sort of pre phase two, and then post phase two architecture diagrams. And really, here we've not made a ton of changes, but some of them are noteworthy. One is that we allow application developers to register custom functions in the pipeline. We can populate views in parallel. And applications can use third-party data access systems because we can sort of put things in all sorts of other data stores so that they can make use of both things. So there's a couple of critical enablers here. That dynamic function registry to load sort of application plugins has been huge. I think this is even better with stateful functions. We have tons of pre-built content that sort of lets application developers push things like pre-built pipelines and those kinds of things, new functions into the process. Because the Firehose is pub sub, application developers don't have to worry about things that people have like filtered out or sort of modified. They can actually get the real deal. And we do auto scale our Flink clusters based on slot availability. So as people start sort of ramping up and doing more, we scale the clusters behind the scenes appropriately so we don't run out of capacity. So at this point, again, like you can imagine the things that we get, really we've at this point offloaded all of those polling operations. And again, in terms of like, we're not doing these things sequentially. I'm just sort of giving you sort of a high level view of this. And we've enabled a bunch of the programming model changes, which is really nice. I am going a little bit faster because I realize I'm running out of time. Real-time query is sort of a really interesting one for us. So being able to do this like live tail stuff. We move our application workloads. What I'm talking about now in terms of real-time query is about ad hoc real-time queries, mostly to humans. So Splunk has this today, but there's some gotchas. It's computationally expensive. It's still better than most systems, but it burns some cores on complex stuff. The data guarantees are sort of really interesting. They're kind of complex unless you really know the nuts and bolts of how the indexers work and stuff like that. So we'd like to simplify that. So, is there a way that we can run thousands of concurrent real-time queries, and with rapid start-stop, people tend to like set up a pipeline, tear it down, set it up and tear it down, sort of modify, like think about what you do when you're sort of like, debugging something in production or something like that. So the short answer is I'll let you know when I do. This is something that we're working on, finding, the most efficient way to do it. We would, I think stay tuned. I think we've actually done some interesting stuff, and I think Flink does have a role to play in this. I would say, you don't want to be naive and just spin a pipeline for each query. It winds up being really challenging. So when you sort of add it all up, working with data, streams are absolutely the right primitive. I got to tell you, it is like lifeblood being able to work with a stream rather than data at rest. And I think sort of chasing your stuff upstream and sort of catching data before it gets into these formats and systems that are sort of hard to work with is the right way to think about the problem. But it is more than just plunk down some messaging, plunk down, a Flink cluster. You really have to think about the semantics, the patterns, and sort of where in the sort of architecture you want these things to add up. The details wind up being incredibly important. People at Splunk have, experience, as I'm sure most of you do, with all sorts of systems, Spark and Flink and Apex and custom built stuff and more traditional stuff like Esper. I'm probably dating myself, but all the traditional CEP systems, as well as tech that we've built inside of Splunk. But things like state management and all these other kinds of things are just like differentiators. I know that we sort of glaze over them, but the fact that Flink does what it purports to do, it's really, really magical. And I sort of, I am so impressed at all times that mostly it sort of just does what it's supposed to do there. I also wouldn't get sort of deeply religiously committed to any one practice or policy or architecture. You've got to evolve as the systems do. And I think stateful functions, by the way, I sort of keep harping on this, but I think it's incredibly brave, for a project like Flink and the community to look at this and say okay, Flink is really good at a bunch of things, but there are real challenges. And so maybe we should think about sort of how we address those rather than trying to shoehorn fast or Lambda style stuff into the existing systems. I mean, yes, you can do it, but like other people have said, that's sort of challenging for a variety of reasons. So I think that's actually really important. So that's sort of what I have. I think I am 38 seconds over. I do see some questions. I would love to connect with folks. There are some really good questions that people are asking about sort of Pulsar and, multi-tenancy and sort of how we sort of deal with those kinds of things. Unfortunately, I'm out of time, I believe. But I really, really, really appreciate being able to be here with all of you today, here for some definition of here. Please stay safe. Enjoy the rest of the conference. I had a blast on the program committee. There are so many good talks. So please enjoy the rest of the conference. Thank you so much. And I'll throw it back to Holder.